And welcome back to another LeetCode video. Today we're looking at LeetCode 1079, letter tile possibilities. And I'm approaching this problem interview style, where I try to mimic the process of solving a coding problem the way I would do in an interview, which means step 1, read and understand the problem. Step 2, ask for the constraints. Step 3, work through the examples. Step 4, come up with one or multiple solutions, including the runtime and space complexity, before writing a single line of code. Step 5, write the code. Step 6, analyze the code with a mental debugger and the example. And yeah, then run through your test cases. So that's what we're going to do. So step 1, what do we have here? Well, we have n tiles where each tile has one letter tiles printed on it. So given string tiles, right? And each tile represents one letter of the string. Return the number of possible non-empty sequences of letters you can make using the letters printed on those tiles. Okay, and the constraints, well, I would ask, how many are there? Are they all different? Can we have repetitive tiles? Can tiles be like a null reference, or etc., etc.? Are there any limitations on the different letters in the tiles or the length of tiles? And the constraints are, well, we have at least one letter in our tiles. And it consists only of uppercase English letters, right? One thing to note, the upper bound is only, if you do a runtime and space complexity analysis and your whole problem has an upper bound on its input, it's always going to be constant time and space. So for the analysis, we're going to ignore the fact that LeetCode has an upper bound here. That's more for practical purposes to make sure the code runs on the LeetCode backend, right? But for the theoretical runtime analysis, we don't care about the upper bound of the input because it makes it less interesting. Cool. All right, so yeah, so now let's work through an example to understand a little bit better of what is being asked here of us. Example 1, we have the tiles AA and B. So we can have duplicate tiles. So we have the tile A twice, the tile B once. And the output for the number of possible non-empty sequences of letters we can make is 8. So this is kind of like, how many different ways can you arrange all the letters in the tiles? But of course you get, if you have tiles twice in it, you don't want to count them twice, I suppose. Let's check. So why is the output 8? So we can have sequence AB, right? AA, AB, BA, AAB, ABA. But you don't see ABA twice. That means, yeah, because we could pick the first A as the first A here, or we could pick the second A as the first A here. But there's no difference. So what really counts is how many unique words we can build. Now, second example. So we have 3 tiles A, 2 tiles B, and 1 tile C. Right, now the number is 188. And if we have 1 tile, then of course we can only build 1 word. So the empty word is not part of the words that we can build from our tiles. Okay, so how can we do this? Well, this is like a combinatorics problem, right? So if we were to, and by the way, one technique is to simplify the problem first, to try to solve a simpler problem. And here it could be, what if we just wanted to count all the different permutations? Or let's say if we wanted to compute the power set of our tiles. Right, this is essentially the power set, except, or is it? This is essentially the power set, but with duplicates, right? That's essentially what we're doing. And I'm just thinking, I'm thinking recursive approach, like a depth first search approach, where we pick a tile or don't pick a tile to put them into our number, into a possible word sequence. Yes. I think that is a good idea. So, oh. Yeah, I think we would have a recursive helper function to do that. And in that helper function, we would so we would loop over all of the letters that we have in tiles, right? And we can either pick that letter next or not pick that letter next. And that means that we also need to keep track of, which letters were already used, which can't we use again. And maybe with that, what could help us is maybe like a hash set where we count, or like a counting, like a hash set that counts how many occurrences of a specific letter we have. So in our recursive helper function, we would just iterate over the letters. And if we have a letter still available to pick, because maybe we had 2 of it and we only used 1, we can pick that letter and then call a recursive helper function. And when we return from that helper function, we will put that letter back. So it's kind of like a choosing and putting back approach. And in terms of runtime complexity, I think, well, we could make it so that the recursion, well, we should probably pass to our, should probably pass to our helper function, at which position are we currently iterating over tiles, so that the stack space is at most O of n. And the runtime would then be, I guess, iterating over all of the letters inside of our helper function. I don't know, let's say we have k different letters, k unique letters, even though tiles has length n. We'd have, I guess, O of k times n, because that's the recursion depth, to the power of k, since we have a branching factor of k in each iterative layer. So that would be, I suppose, my approach. So that'll be O of, let me just write down the runtime complexity. O of k times n raised to the power of k time, and O of n space, where n is length tiles and k is unique number of. Right. And we would have maybe to initialize, I guess, this hash set with the counts, where we have to iterate over, over all of the tiles, which would be O of n. But since k could be, what is the value for k? Well, the number of different letters is at least 1, so we don't have to add it here. Right? So yeah, so that would be my approach. Does it sound good? Yes or no, Mr. Interviewer? Yes, sounds awesome. Okay, cool. Let's implement this. So we're going to implement first building our letters countering thing, right? Letters, we're going to initialize as an empty set for, I guess, C would be letter for C in tiles, and just say if C not in letters, we put it in there. And the count is going to be 0 initially, but of course then we're just going to update it was equal 1, right? So that's going to be our initialization helper. I said we're going to pass in an index, and that should return us the count, right? So we need to we need to call that helper, start at index 0. And well, what is the base case? I don't know yet. But I know that we're going to compute like a number. How many different ways are there to combine the letters, right? So Yeah, well, well, the base case, I have to think about that one. I'm not 100% sure yet. But I know that we want to iterate over all of the letters inside our helper function, right? So for C in letters, if letters at position C is larger than 0, that's otherwise we can't use that letter, otherwise it's already used. If that is the case, then we will maybe decrement it, and we will have our recursive call, and after that we will increment it again because we want to put it back so that the letter can be chosen at a later time as well, right? And we're going to update our result by making the recursive call. And we're going to say, okay, but we now have to use the next tile, so to say. Well, it's a little bit misleading, but I iterates over the number of tiles, but at every position I, we choose any of the remaining letters that we can. So we're not choosing exactly the tile at position tiles I, right? Just to make that. So, right. So now we have to think about the base case. And when should we terminate? Well, if I is larger, I larger equal length tiles, well then what should we return then? Should we return 0? Well, if I is smaller than tiles, then we can iterate over the letters, right? That's what we know. Now, if I is equal to 0, I'm just thinking because I think there's an edge case here. When we call it with 0, when I is 0, we don't want to count. Well, the thing is, when I is 0 means we haven't picked any characters yet from the letters that we have available. So saying that in the base case, if I is 0, that means we need to initialize our result with 0. Otherwise, when we go into the recursive call here, then I is not going to be 0. And the current word that we already built by choosing a letter counts as a word, right? So, so what we have to do is do it like this. So result is 0 or 1, depending on whether I is larger than 0 or not. Yes, otherwise we would get an off by 1 error. So the base case differs. No, wait, actually the base case, talking about base case, the minimum result is going to be 1 when we're in a recursive call, and the maximum minimum and the minimum result is going to be 0 when we just made the first. That's what that is. And the base case is that we just return the result and we don't go to the recursion. That is when we've reached the end of n, when we've reached the maximum. Otherwise, we have to keep iterating. I think now you can also see why the complexity. So we have k times, because we have k letters. This loop is the O of k. But recursion def is O of n. And at every step, we have a branch vector of k, which is why we get n to the power of k times the effort for each recursive call. Okay. So now let's go through an example. Maybe let's use the input example 3. So tiles is v, so we build our letters thing, and it'll just contain v and a count of 1. Now we start with the helper, and we initialize it with a first call of a 0. That means our res is going to be 0 in the beginning. And now it's smaller than 1, right? Length of tiles is 1. So we're going to iterate over all of the letters. Obviously, there is only one. So letter is going to be V. Count is larger than 1. We're actually decreasing the count of V to 0 here. And then we call the helper function with I plus 1, which is the value 1. Right, so now I is no longer smaller than the value 1. However, it's larger than 0, so our result is going to be 1 in this case. And we're not executing this part of the code since I is the length of tiles. We return 1. Then when we come back from the recursion, we increase our result to 1. And then no other letters to iterate over, and we're done. And then we return the value 1. So for that example, that worked. Now let's try this other example. So we initialize letters with A. Obviously A will be 2 and B will be 1. 2 A's and 1 B. Now we call the recursive helper function. So I is going to be 0. Res is going to be 0 as well because we're in the base case here. Now length I is smaller than 3. Right? Length of tiles is smaller than 3. And now we iterate over the letters, maybe A first. So we would pick A, we go into the recursion. In the recursion, res is now 1. Its our comparison is now 1 smaller than 3. Now we iterate over the letters again, and maybe we run into another A. So we just counted here the string with the letter A as one possibility. Now we're adding another A, so we get to this string, make the recursive call, and then we make another recursive call, and then we reach that string A. Now we unravel the iteration, and we're back at A, and now the next one that we pick is B, and then ABA, etc., etc. So I'm shortcutting this a little bit. To me, that is clear that this will work. Maybe I should have just used that example to walk through it because I don't know, but you know, it can be quite time consuming. So pick your examples carefully and look at how much time you have in an interview. Right, I'm just going to make another scan through the code real quick to see if I have any obvious syntax errors. So that looks good to me, iterating over the tiles. That looks okay. That I'm looking at the colons, that's where I always make the mistakes, and the methods that I use. Helper, we call helper correctly. We're taking a number out, we're putting it back in. Looks good. Yeah, I think. And this logic, by the way, I don't know if you've seen this before. So if this evaluates to true, we're going to pick the result at index 1. If this expression evaluates to false, we pick that at index 0. What that does. And then we return the result. Right. So I think that looks good. So I'm just going to submit it to the test cases. In an interview, I would say, I'm confident that this will work. Blah, 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 blah. So, and now we see it actually does work, at least on the test cases. And now I just submit the code and see that it passes all of the tests. And it does. Right. So, yeah, I hope that was somewhat insightful. The point is really to practice the systematic approach, and another reason of why I'm doing this, creating these videos, is to force myself to talk through code, which makes me better at interviewing. So that's the whole point of that. Yeah, and I encourage you to try something similar.